But first, like one question I'd like to just throw out to everyone, because I heard that you came across the project. You guys, I understand, are mostly working on the prover or on crypto libraries, and I was wondering, kind of like where the interest, or whether you already had questions, or kind of where did this come from? Anyone willing to open up? If not, it's fine. All right, then I'll just go straight into the presentation, and we can break the ice. So let me see if I can share. Let me see. Present. And like I said, this is a presentation that was already given, so I might gloss over a few of the things, jump over whatever. I'll just. Aniket, go ahead.
Yeah, I recently came across a post where Fairday posted the stats of Cairo VM compared to Cairo Native, and it was much faster. And that's recently, that's where the curiosity came from. And yeah.
Excellent. So that'll be a good point to talk about. Why is it faster, right? Motivation. So we'll jump right into that with the presentation. So the project used to be called Sierra to MLAR. We'll go into why. We renamed it to Cairo Native. But basically, the goal of the project is to take not Cairo code, but Sierra, which is an intermediate representation. It's like the same, but transformed by the Cairo compiler. And to take that code and execute it and get a result. And to do that faster, basically. So like the end goal of the entire project is not really a compiler or how we do it. It's actually to just run Cairo code faster. Why would we want to run Cairo code faster? Well, usually what we expect is for Cairo code to run as part of handling a transaction, right? Or in some other context, but basically you want to run a Cairo contract. You want to prove something about that transaction. But first you need to get the result, and first you need to make sure that that transaction is valid. There's a whole bunch of validations that you need to do as part of a network before you actually get to proving stuff or verifying. So remember this, because this motivates a lot of the design decisions afterwards, right? So the goal is to actually make transactions go faster. How would you make transactions go faster? Well, the current way transactions are handled are you get the transaction which says, please run this function from this contract with these inputs, and you have to take that program representation, run it through the Cairo VM, and the Cairo VM will give you the result of that, and it will also generate the trace you need to prove it. So a lot of things are involved in that are not really necessary in just the context of making the transaction go faster in a sequencer, right? So to make sure that it's valid, all you need is a result. To make sure that it uses, that it has enough gas provided for that transaction, you just need to know how much gas it used, and so on. So that's the first thing. You need to do less work in that context than to just prove the results. The second thing is that the sequencer doesn't need to actually use all those resources. The interpretation in a virtual machine has an overhead that uses CPU, and also generating that entire proof requires memory. You don't need that either. And there are other use cases as well, like, for example, developer toolings. And in that case, also, there's a bunch of work that is not necessary. You just want to make sure that your contract is correct as you're developing it. And then once you know it's correct, you can, deploy it. So like I said, the end goal of the project was to make things go faster, and then integrate with another project like a sequencer via the execution engine, the Starknet and Rust library, which is the logic for handling all the transactions. So Cairo Native is just make Cairo code go faster by doing less work, first of all, and then by compiling it to native code with compiler tooling. and then to put that into an execution engine and make that go faster. So it's not to actually prove. So that's one important thing. We do not generate an execution trace, and it's not to replace the VM, because you can't do that, because you need the VM to do all the other checks. So we also don't have, for example, built-ins and so on. So that's the why, the motivation around it. Any questions around that? Good. The next is, okay, how do you do that? Well, like I said, first of all, less work, but also we want to get rid of the interpretation overhead of having a virtual machine that takes bytecode or some kind of bytecode as its input, and to run it natively as CPU instructions, right? So what we have to do is we have to take the Cairo program and somehow transform it into like a binary executable and run it, right? In the context of something also that will handle a bunch of contracts, a bunch of different transactions with different inputs and so on. So looking around, if you want to do that, if you want to take a representation of a program and turn it into machine instructions, what tools do you usually have? Well, first and foremost, LLVM is like undisputed king today of code generation. Actually, the project started using LLVM to generate code. But one thing we noticed was that in the LLVM space, there was like a parallel thing happening, which is that LLVM has become used for many different types of applications. Some of them are, as you know, there's a lot of development in AI, in machine learning, and most of machine learning is basically tensor algebra and matrix multiplications. And so they've tried to take code that does machine learning and run it on different kinds of CPU with better CPU architectures like TPUs or GPUs. And in the process of trying to generate code for those applications, they ran into that LLVM was not really like a good tool. And why is that? I'm going to like gloss over all this, but basically everyone was just like re-implementing stuff again and again for every kind of architecture, compiler, machine learning framework, and so on. So there was a lot of code duplication, and also LLVM was not like the proper level of abstraction. If you've ever worked with LLVM and its representation of programs, it's basically an abstraction over assembly, right? You've looked at assembly code for a certain CPU, like x86 or ARM. It has a lot of assumptions of what that CPU does and how it works, and what those instructions look like. LLVM abstracts over all those different families, gives you like an abstract machine, but it's still like an assembly. It's like a linear sequence of instructions. Then it's still like the main abstraction in LLVM is a CPU instruction. But you're trying to always, when you compile something to LLVM, to its intermediate representation, your concept is CPU instruction. If you can translate it to something like that, that's fine. But if not, it becomes more complicated. And in the case of machine learning, when you have tensor operations or linear algebra operations in general, many of those situations were not like this is just a single operation. And also, it's not a single operation that you can abstract the same way in different types of hardware. So what they came up with was a separate project from the same people that make LLVM called MLIR, which is a multi-level intermediate representation. And the idea of that is to do basically the same thing that LLVM does, but on a higher level of abstraction. So so instead of saying I have a CPU instruction as like my core concept, what I'm going to do is I'm going to say I have operations, and those operations can be much more arbitrary or general than just a CPU instruction. But it could be the case that an operation translates to a single CPU instruction, like an integer or a floating point addition, something like that. But then it also provides a lot of very high level and very abstract concepts to join all that together in glue, right? So if you have an operation kind of modeling anything from, let's say, a felt operation, operations on elements within a field, or within linear algebra, or just a single integer within a CPU. Anything of that could be an operation. If you string those together, that's a block, a sequential list of operations. And if you have like a graph of blocks representing control flow, if you have an if or a repetition via a loop, then that's a region. And then if you put all those together into a module, that's a type of operation that just abstracts over everything. Then you have something that can represent computation, any kind of computation, any kind of program, in different levels of abstraction, right? Because some operations might be very low level and some operations might be very high level. And then what you can do is you have use the concept of conversion between one operation and another to translate between them, right? So you might say, okay, I have a program. It's a Cairo program. It has this type system, these user types, these user values. I'm going to represent them in a certain way, and then I'm going to lower them and translate them into operations of a different kind. And we'll see more or less how that's done afterwards. So we saw that MLIR was a better fit, and we started using that to translate the Sierra representation of a Cairo program into these operations, regions, and blocks of MLIR using this library. The good thing about that is that it comes with a bunch of things built in. One of them is these dialects, which are like sets or groups of operations that are logically related between them. So, for example, you have anything that's basic arithmetic will be in the arith dialect. Anything that's control flow, like an if or a branch, will be in the CF control flow dialect. But then there are many other dialects that are not listed here. But one of the important ones is LLVM. So everything that is LVM, like the old LLVM, is also represented within MLIR as a dialect. So what we can do is we can take our program in memory as data structures, translate that into operations within MLIR from all these different dialects that come built in, and all these dialects have a conversion into LLVM dialect. So you can translate that from your language into MLIR dialects, and from those MLIR dialects into the LVM dialect. And then once it's there, you can say, LLVM, please lower it and apply all the optimizations and all the program transformations that come with LLVM, which is a very mature and battle-proven and industry-standard library for transforming very low-level operations. So you get all that for free, basically. It's very easy to use. So then the question becomes, okay, so how do you translate Cairo or Sierra into these things, right? So for that, we need to to understand that, we need to look and understand what Sierra looks like. Have any of you taken a look at that, read about it? Do you know what Sierra is? Can I take like a parenthesis to explain that?
Yeah, sure. Maybe it's good we talk about the prover, but not perhaps as the way you go from Cairo code to Sierra and then down.
Right. Let me look for a different graph here. I think it's more like at the end of the presentation. This one. So this is more or less how Cairo code is compiled and run today, right? You have a Cairo contract, and when you run Cairo compile or Starknet compile, which are the two interfaces to the compiler, on that user written code, internally it gets transformed into this Sierra thing. What is Sierra? It's a safe intermediate representation. From there, the compiler will do is transform it into CASM, which is the Cairo assembly, which is the input to the Cairo VM. The Cairo VM will take the CASM representation of that original Cairo program, run it with the input, generate a proof, and give the result, right? In our case, what we do is, instead of translating into CASM, we translate it into MLIR, from there to LLVM, and from there to a machine native object code. So that's kind of like the pipeline, right? But before that, I think it's very interesting for everyone to understand exactly why Sierra exists, for two reasons. First, it's relevant to the prover, and also because it's a very good like case study in language design. What motivates language design nowadays? Why we're seeing so many languages and compilers pop up in the crypto space, for example, when it doesn't happen in other areas. So if you know anything about the history of how the Starknet or Starkware software stack was developed, more or less, it starts like a bunch of years ago when they started developing the crypto primitives, and they say, hey, we can take some information, not a program, but some information, prove something about it. So they developed the crypto primitives, and they saw that it was all good. But what you had to do was, for every single problem that you had to, somehow you're on your own, translate how it would convert into like operations, right? Cryptographic operations. In other areas, where you use circuits, you would say that you would have to, for your problem, you have to build your arithmetic circuit on your own for each one. And that's what they did, actually. In the very first iteration of Starknet, they built the Starknet OS and the Starknet, like the network. They did it by hand. And it was great, but when they started getting clients that said, hey, I would like to do this exact same thing, but in this other application area, or slightly tweak it, they would have to, by hand, do the crypto stuff again. So they said, this is first inefficient, it takes a long time to do, but even more so, it's very scary, because only we can do it, and there's no guarantee that you won't make a human mistake in that translation, and you end up proving something that is not related to your original problem. So how do you get some guarantee that you're actually applying the crypto correctly to your problem? And that was something that they thought very hard about, and what they came up with was the Cairo VM. The motivation for the Cairo VM is to have a regular input that can be proven, that is correctly built, and then generate a proof on that program representation, on that problem representation. And that was Cairo 0, like the very the previous iteration of the language. It still looked like assembly, but it was still much easier to write a program in this Cairo VM assembly than to actually build a circuit on your own. That was an improvement. But it was still error prone. Why? Because you still have to make sure that the input to the Cairo VM is provable. It's a good program to prove. There are many things that you have to check, that you have to make sure that are responsibility of the programmer. Among them is proper resource usage, that you don't generate an infinite loop in your program. There are many reasons that could invalidate being able to generate a proof for that program. So they said, okay, what we need is a series of guarantees on the program that come given, that need to be checked before you give this input to the Cairo VM. And that's how they. And also, in parallel, people didn't want to write contracts in something similar to assembly, because it's hard for a user, for a human, to do that. So what they did is they came up with the new version of Cairo, much more high level, with nicer data types, similar to Rust. But you still have that problem of saying, okay, I now have this full-fledged programming language. It's easy for humans to use, but there's a subset of programs that you can write in Cairo, in the new Cairo, and there's a set of programs that you can prove. How do you make sure that there's, first of all, overlap, and a good overlap between those two sets, and it's not something that it's very difficult to reason about? So that's where Sierra comes in. What the Cairo compiler does is it takes the code written by a human in Cairo, it translates that to Sierra, and at the Sierra level, verifies a bunch of things. It will verify, for example, that you cannot divide by zero in any arithmetic operation. It will verify that your resource usage is proper, so that you don't use memories twice, so that you don't use the segments in the what you need to prove about twice, that you can consume it only one time. It will make sure that all your programs are terminating and that they will terminate. It will make sure that the gas is accounted for correctly and so on. So once you translate from Cairo to Sierra, if you can correctly translate from Cairo to Sierra because your syntax is correct, because your type system declarations are correct, your semantics are correct, if you generate Sierra, the equivalent Sierra program for a Cairo program is one that has a bunch of guarantees built in. And so with those guarantees, you can now move on to the problem of generating the CASM, the assembly for the Cairo VM. So that's the motivation for Sierra. That means that we as users of this tech stack benefit from translating from Sierra to MLAR and to native code, because it's already been checked for a bunch of stuff. There's a few checks that we have to do on our own when translating from Sierra to the object code, but they're much simpler to do. Does all that make sense and kind of mesh with what you've seen so far?
Sorry, I have a question. If you go back to that diagram that we were looking at, can you explain again where Cairo Native comes in? And you said it's in the sequencer, because I guess my sort of naive understanding is just the first thread, so Cairo to Sierra, Sierra to COSM, and then the Cairo VM outputs a trace. And so where exactly are we using Cairo Native, and what is it used for?
Right. So in this very simplified graph, this is still just like saying, okay, I have a program written in Cairo and I want to run it. Right. It's not contemplating the network. It's not contemplating the execution engine or anything else. But if you were to take a Cairo contract and run it in Starknet, you would need, in addition to just the VM which will execute the logic, you need to know about blocks, contract hashes, contract addresses, events, and so on. Those are all concepts related to the network, right? To Starknet, and not just. So that would be like in a box outside containing all this. And so in our context, what we would, or in that context, I would say that what happens is in Starknet in Rust, or in a sequencer which uses a Starknet in Rust, what happens is you get the transaction. The transaction says, these are the inputs, this is the class hash, please execute this is the gas that I have in this count. It'll move it through all the state machine, representing the changes to state, reflecting running that transaction. And it will, if everything checks out, run it through the Cairo VM and give you the result, and that will be part of the state diff in the Starknet, right? Cairo Native, where it would fit in there is for the very first time that you get that transaction, you want to validate it, right? Because one of the things you need to do is you need to very quickly and very cheaply not do all the work for invalid transactions. Because if the lower your cost for that, the higher tolerance you have for things like DDoS. Someone flooding the network with invalid requests. If it's very expensive to check for validity, then you can check less transactions. So Cairo Native would be at the very first gate and say, I can run this. Yes, I can run this. The result is okay. The gas is okay. Move it forward into the pipeline and actually execute it on the VM and generate the proof eventually. That would be like where it fits in the higher global picture. Does it answer your question?
Yeah, that makes sense. Yeah, thank you.
Great. That's just like a higher level. All right. Sierra. What does Sierra look like? I have a very simple example here, which we can walk through. For this function, right? This function in Cairo, what does it do? It takes a felt and it returns a tuple of two felts. And what it does is it adds 2 and it subtracts 2 from your input. It's a very simple function. It doesn't do anything useful except serve as an example for the following. What does the Cairo compiler do to this function? it translates it into this. And I'm sorry for that, slide, but this is, par for the course with compilers. But I can break it down. The Sierra representation of a Cairo program is actually very structured. It has first a bunch of types declared. And you'll see, for example, it'll say, well, we're using the felt 252 type, right? Then it'll also say, I have a tuple of 2 felts of this type. Why does it have all the types declared in each and every program? It's because you won't have all these basic ones, but you'll also have all the user ones and everything that was built up in the process of compiling the program, but also because many types in the language are actually generic. They have like a type parameter, right? So not in this particular case, but you could have, for example, a felt of different width. It's not the case in reality, but to illustrate as an example. And in this particular case, we want the 252 one, the one with 252 bytes. So first you need to say, okay, these are all the types that are used in this Sierra program. After you have the types, you need to declare also the specialized library functions. So what happens is in Cairo, you will have all the user types, you will have the functions, you will have the contracts, you will have within the functions expressions, ifs, whiles, function calls. You have another function and you call that function. All that is represented in a different manner within Sierra. So everything that you can do within Cairo ends up being one or more library functions, they're called. And in this case, you can see that we're using very few. What we have is a function, right? But let's go back to the original program. We have a function, we're building a tuple out of it, we're adding and we're subtracting, and we're returning it. That's basically everything this program is doing. So what library functions do we need to do that? Well, you can see here that we have felt 252 add, felt 252 sub. Those are pretty basic. We have struct construct, which constructs in memory a tuple, and some other internal machinery type stuff like a dupe and store temp, which also manipulate memory basically. But after you have your types and your library functions, at the very end you'll have the entry point into this program, right? So you say this was a simple function. It's called simple program. Our function was called something. So the entry point is simple something, right? And it has also the type signature of what it takes as input and what it returns as output. And then this is the all-important part, the sequence of statements. So this is the representation of the instructions in Sierra. And also you can see it's not that much, but it is like 9 instructions versus 1 line of code for the function, right? So, but we can still walk. Let me see if I have a bigger. Yeah, this one. This is just the statements. And it's not too complicated. You can see that the very first thing that you do is you declare a felt 252 constant with a value parameter, which is 2. And you say, okay, this goes into memory segment 1, memory location 1, sorry. I need to duplicate it, what's in 0. Oh, by the way, the one in 0 is the input, so that would be our A in the function, our input, the thing passed in via parameter. I want to duplicate that and put it into another memory location 3, so now we have 0, 1, 3. And I want to add what is in memory location 3 to memory location 1 and put that into memory location 2. So that's the first add, it's A plus 2, right? So we put 2 in location 1, we have our input in location 3, we're adding them to those 2 together and we're putting it in 2. Then we need to do the second part of the tuple, which is to subtract. In this case, we're creating another constant. Could it be the same constant? Yes. But the compiler in our case has generated this sequence of instructions. It could be more optimal, but it's not. It's also not too expensive to do this. But this could be, for example, just to reuse the same constant. But we're building another constant with the same value. We're putting into location 4. We're subtracting 4 from our original input and putting that into 5. Then we construct the tuple, we store it in a place from which we can return it from, and then we return it. And that's basically everything. Of all this is in Sierra, remember, we're still not in Cairo Native. This is our input. This is the input to the Cairo Native compiler. And instead of compiling the entire program, because that would take forever, we're just going to take one library function, which is how it adds two felts. This is the MLIR representation of that. So this is the output of our compiler for that single library function. I know this is hard to read, but the first thing that stands out is these large numbers, right? What are they? Does anyone recognize them? It's the prime for the field. So what I'm going to do to make this easier to read is we're going to, instead of using this very large prime, we'll just use 43 and be called it because it serves the same function. So as you can see, the MLIR representation of this library function, felt252add, takes two arguments, obviously, right? It takes arg0 and arg1, and those are represented, these are now MLIR types or LLVM types, an integer of 256 bits. That's how we're representing them in our version, right? Has a bunch of stuff that we don't need to worry about, but it says it takes two arguments, arg0, arg1, returns an I256. The very first line, here, is saying, I want to add them. It's straight up just emitting an add I, an integer addition operation, from the arithmetic dialect. It's passing in the two arguments, the same two arguments from our function, and storing that into location 0, a temporary variable called 0. But this is not no ordinary integer addition, is it? This is, we are operating on field elements. So what we need to do is we need to make sure that we're still within our field. So the next thing that we do is we're going to check if the addition, if the result of the addition is greater than our prime, we can do this hack and say, well, we can just subtract it, right? And make sure, instead of doing the modulo, we can just subtract the prime. So we have two basic blocks. That BB is for basic block, and remember that a basic block is just a basic sequence of instructions that are sequential. They have no control flow within them. So basically, this is just a big if. If the addition overflows, then subtract, and if not, just return the value. So you can see here that the first instruction is to declare the prime constant. The second is CMP for compare CMPI, compare integer. And you want to do the integer comparison of the constant and the value in the temp variable 0, which is the result. And you store the result of the comparison in another temporary variable called 1. If that 1 is like true, condition BR is for conditional branch, conditionally branch on the value within location 1. If it is so, jump to basic block 2, and if not, jump to basic block 1. And in basic block 1, you're going to just return the value because all is good. And if not, you're just going to do the integral subtraction of the constant, the C43, from the value. And that's it. So you can see how what we're doing here in Cairo Native is taking a higher level operation, which is a field element addition, and lowering it into more operations of other dialects. We have add I, we have a declaration of a constant, we have a comparison, and then we have the subtraction, right? So that's how we map from one level of abstraction to another. And then once it's done here, we can just add, since it's already within an MLIR dialect, we can ask the MLIR library to just translate that to LLVM, and from LLVM to apply all the optimizations, and then lower that to machine code and actually execute it. Does all that make sense, or was that?
What is that? The assembly version of Rust, or what language is that?
So what you're looking at here is the textual, human-readable representation of MLIR. It looks kind of like assembly, but it is higher level. It's even higher level than LLVM IR. But this gets translated to LLVM intermediate representation, and that gets translated to the actual assembly, and then the actual assembly gets translated to ones and zeros that the CPU can execute.
How does going from MLIR to LLVM and then to some output that could be fed into the virtual machine is faster than just going to LLVM? You have one more step added to it.
How could it be faster?
Yeah.
Sorry, I forgot the pipeline. Can you repeat the question very briefly?
Yeah. So in one of the previous slides, you showed that there was going to Sierra and then to Chasm and then to virtual machine.
Mm-hmm.
But on the right fork, there was going to MLIR, then to LLVM, then to some object. How is that faster? Because you have two more.
No. Well, the process is not. We're not comparing the time of these two processes. This would be like the compilation, right? So this is before you actually run anything. What happens is that the end result of all this compilation process are two different programs. One will be Chasm,
right.
The other will be a native object code. And running the Chasm and running the native object code is much faster in the native case because you don't have to run the virtual machine.
Yeah, I see. Thanks.
That's the reason. So it does take, whether going straight, like the time of going to actually reaching the VM might be slower. Might be faster. But once you reach the VM and then you have to actually execute your code, it'll might be much slower in that case. And you only compile once, really, or a few times, and you actually run, hopefully, millions and millions of transactions in production, right?
So, I want to ask that the time that we are comparing now, is it the time for running it at the on Ethereum, or I mean on the settlement layer, or where is the object or the Chasm going to be run?
You mean like the actual object code? Where is it run?
Yes.
So that's being built still. So that would be more than in Cairo Native. It would be at the integration of Cairo Native into an execution engine, correct? So if you have an execution engine like Starknet and Rust that is embedded into a sequencer, the sequencer has to store in its database all the class, the class code, right? So in this case, it would be the same. Instead of storing the class, like the class Chasm, it would store just a native object. And then when it says, please run this particular contract, it would go and fetch that object and run that function from there. So where it really depends on how the sequencer node is implemented. I'm not sure if that answers your question.
Yeah, I understand it better now. I have another question. Will it be operable with one another? And the contracts that are already deployed using Sierra, will it be available using the Cairo Native?
Sorry, I'm not sure I understood the question. Can you repeat it?
So I'm asking that will it be interoperable with one another? Like contracts are already deployed using Cairo VM. Will it be can it be accessed while proving some other transactions using the Cairo Native?
I see. I think I understand. So, like you said, currently what happens is that I think most contracts that are deployed as Chasm, right? The newer versions of Starknet allow for deploying a contract not as Chasm, but as Sierra, right? So instead of this step, you have one before, and then in these newer versions of the network, what happens is that the sequencer compiles the Sierra to either Chasm or to the Cairo Native, right?
Yeah, that works.
So
That's
yes,
a better level of abstraction.
that's a change. I think exactly, you need that higher level of abstraction. One of the major changes we made to Starknet and Rust to be able to integrate it is to make sure that you can actually have the Sierra there for a contract class, right?
Thank you very much.
Okay, so this would be more like high level, conceptual, what it is, why it is, and very high level how it works internally. Another thing I can, let me see if I think I'm sharing. Let me see if I can share the window. Window this meet. So that was the presentation. This is the Cairo Native repo. In the README, if you want to play around with it, the main requirement you have is to have LLVM installed. If you're developing on a Mac, you can just go brew install LLVM, and that should install LLVM 17, which is a version that we're currently using. The only thing you need to take into account, please read the README, is since on Mac OS, Mac brings its own version of LLVM, and we want to use this version, what you need to do is you need to export these environment variables so that it finds the correct version. And once you do that, you can make deps and cargo build and start playing around with it. Cairo Native is mainly a library, but it comes with a few command line interface tools that are easy to use. One is you asked about that, what we were looking at, whether it was assembly or not. That's MLIR textual representation. You can see that by using Cairo Native dump. And if you want to just run a program, you can do Cairo Native run and just give it a Cairo program with its input. This will be a bit more complicated to build, but there are examples. So you need to give it the program that you want to run, the Cairo file, the input, and the entry point into that program. Sorry. One of the difficulties we have is how to pass in felts at the moment. So you can't pass in just like the value and then we convert it. You have to pass in all the limbs. That's something that we need to change as soon as possible. But there is an example of how to use the API, the main API, in the README. There's also another developer guide, which has a bit more in-depth, a few more examples on how to run it and how to use it, what the basic workflow is like, and also what an overview of the compilation workflow and how it works. So this is more like internals if you want to run it. And then there's also extensive doc comments with examples as well. So if you're on Cargo Doc, you get this, and it should be a bit more. I don't want to click on anything that's not documented, but it should be documented. If not, just raise an issue. But another very interesting thing, once you read the README and the developer guide, there's this folder called examples. These examples are examples of how to use it. The very first one is the easy API, which is it's actually an easy example of how to use the API. We can very quickly walk through this because it's very simple. We have this program called Hello Cairo. And what it will do is we'll just load up that Cairo program. It will compile it to Sierra for you, so you don't have to compile it beforehand. And then it will build up all the data structures that you need to compile it. So it has a native context. This wraps all the machinery of our compiler, the actual compiler, the MLIR data structures, etc. You need a native program, which will be the representation of your code. Once you compile it, it's in there. And then you need to do a bit of setup to say, I want to actually call it, because you need to set up the inputs, the entry point, the parameters, and this function ID is a selector for which function of your program you want to run, and this is how you actually invoke the native executor to actually run it. This example doesn't go much into returning the values, like examining the return values, but the other ones are more a bit more complicated, but also more in depth in how to deal with that. Would you like me to go into more depth around any particular aspect, or do you have any other questions?
Is this Cairo Native code only for the Starknet and Rust sequencer, or is it for?
That's a good question. That's a good question. So we can compile arbitrary Cairo programs with an asterisk. Why? let me show you why. Because that's a good question. So remember how I told you everything in Cairo gets translated to Sierra, and every Sierra program is basically just a sequence of libfuncts or library functions, right? So I just showed you like 3 of them. There are over 150 different library functions, and our compiler, to translate all of Cairo code, needs to be able to translate all the library functions, and we don't have all of them yet translated, right? So there are like bits and pieces that are missing, but usually if you go into the repo, you'll find in the examples folder and in the tests, we take the core lib, we download it, and then we compile the entire core lib to make sure that we can compile basically anything. But a Cairo program is not the same as a Cairo contract, right? There's like a few extra bits that you add on. You have the entry points, you have the views that are different from other functions. You have the things that emit events and all that. So those are concepts relative to Cairo contracts, and those, of course, are tied to Starknet. I think the goal of Cairo and the people developing the compiler is to take it in a direction in which both Cairo, Sierra, the library functions, the VM, all that should be as independent of Starknet as possible, right? However, you actually need some way of bringing those concepts into your program, right? It can't be just like a wrapper around it. It needs to be inside of it. So there are library functions that are specific to Starknet. I would say, like, as of today, both Cairo, the Cairo compiler, Sierra, the VM, all that is quite tied to Starknet, and if not, it would be like it depends. It depends on certain, like on what you're using and what you're not. But today, I would say yes, it's tied to Starknet. Although you can run like arbitrary programs. In our integration efforts between Cairo Native and Starknet and Rust, what we try to do is we try to make interfaces that are then implemented for Starknet and Rust. As you know, there are 2 execution engines, right? There's a Blockifier, which is the one that's run in production net, and Starknet and Rust, which is our implementation. So currently, Cairo Native is only being integrated into Starknet and Rust. Once that gets more mature and fleshed out, it will be eventually integrated into Blockifier, and Blockifier will have to implement the same interfaces. However, those interfaces are kind of like predicated on all the concepts within Starknet and not another L2. If you wanted to build your own L2 with the VM and Cairo Native and stuff like that, you'd have to rebuild a lot of stuff. Does that make sense?
Yeah, and how much of a performance improvement is there using inserting Cairo Native into this?
It depends, and we're still trying to figure that out. So when we first started measuring we were only able to measure, for example, very small programs that were CPU bound, did nothing but just crunch numbers. If you're in that space, you can get anywhere like 300x, which is a lot improvement, because you're just crunching numbers versus in the CPU versus interpreting every operation for crunching those numbers and then doing the number crunching. If your program is more about building a lot of values in memory, you'll still get a speed up because you're not going to be additionally allocating all the memory of the trace, but your speed up will be less because you're not just number crunching anymore. So if your program is CPU bound, you should get a higher, anything between 20x and 300x. If your program is more general purpose, then it'll be more in the range between 5 and 30x, depending. And another thing that we're trying to measure now is the impact of just running a program for a long time versus what is the actual speed up of running a transaction. Because usually transactions are very small bits of code from a larger contract, right? Like just move this value from this contract address to another, or calculate the state diff. It's not a lot of computation. It might be the case that in those contexts, the speed up is not as much, and we'll get just a percentile difference or just a few x under 20x difference, like 10x difference. That's what we are expecting.
Yeah, I think that's an important point to remember. I think when we run a contract, we're typically running functions within the contract, not the whole thing.
Exactly. Yeah. It's interesting that when we started writing our benchmark suite, we do like the typical, Fibonacci with 1,000 elements of Fibonacci, 1,000 elements of factorial. Those are basically addition tests. But then we started doing stuff like multifactorial that build up a tree of values in memory. And what happened was that when we got into the higher numbers, like for 10,000 iterations, Cairo Native would do it in just a few milliseconds, and we weren't able to measure how long it would take the virtual machine, because the equivalent in the virtual machine started allocating 60, 90 gigabytes of memory for the trace. So it's not also just memory speed up. Remember that it's both memory and CPU usage that you're reducing by using Cairo Native. So also take into account that since you still need to generate that program in the end, you won't be able to prove it, right? So it's kind of like what speed up you can get is like you have to take into the global context. It might be possible that you can validate it very quickly, and then down the line, it turns out that you weren't able to prove it anyway because it's just too expensive.
But in terms of Cairo Native is just for pre-checks, the use case of it in the sequencer?
Pre-checks, yeah, well, that's the initial. Also for developer tooling, that's the quality of life. But mostly it's just to make the TX go faster.
So it's more than just catching invalid transactions.
Yeah. Remember, it's you could probably get a similar speed up by just doing less in the VM, but you'd have to refactor the entire VM. And once you do that, which is basically a rewrite, you would still not have the benefit of actually running native machine code.
Oh, okay. Yeah. What how far along is the project?
We're trying to wrap up the integration. So like I said, let me show you the window here, this one. This is the Cairo Native README, right? At the very top, we have this list in the implemented libfuncs and the ones that are missing. I think this is pretty much up to date. So we're missing these implementations. Another thing that we're missing is for the Starknet, that for the integration is an implementation of something I haven't talked about at all, which is imagine this: you generate a contract, right? You write a contract, and the contract has a function that says call this other contract. So that's a syscall, right? That's something that it's not part of the program. It's something that the program has to ask the operating system of the network to do for it, right? Please call this other contract, instantiate it, run this function, and please return the value that it gives you to me. So that's a system call. And we need to have a way for the programs that we generate to be able to call those system calls. In the VM, a syscall is a type of built-in, as I understand it. What we did was we implemented a different type of interface so that the code that we generate calls into the calling the context, and then from there trampolines into Starknet and Rust code and can actually do all that stuff. We're still missing a few of the implementations of these syscalls. So for example, in this list, you can see here that we have a bunch of them related to the SECP 256 curve, right? All these are all basically just calling a library implementation of that curve, right? But it doesn't do it within the program. It asks the execution engine to do it for it. The same thing for deploying a contract, for emitting an event, all those system calls, related to network concepts. All that is done outside. So we've finished implementing most of them. We have an example of the ERC20 contract running. If you go to Starknet and Rust, you'll find it there. I would say overall it's like 80% done, because what we're missing is these remaining library functions, the remaining syscalls, and then a few, mostly it's polish to make sure that it's production ready. So one thing that it's like not easy to use yet as a user, but one of the things that is very important is if you're running code that is provided by an anonymous agent in the network, you can't really trust it, can you? And it's one thing to take that code, compile it, and then run it on a virtual machine, which is by definition a very containerized execution environment, and another is to translate into CPU instructions and run that. So it would be very easy to just convert Cairo Native into basically an attack vector for hackers. And get it to give you access to stuff that it shouldn't. So one of the things that we need to do is to sandbox the processes that run those contracts in a different process, and then do back and forth with the results. That's one thing. And then another thing is we need to add in a few more checks to make sure that the resource usage is limited, so that you don't do stuff like write a program that it would never be provable, but you could run it in Cairo Native and blow the stack, and by blowing the stack, get access to something. So those are a few things that we still need to implement, but we're kind of like wrapping up. Most of the functionality is already there.
Cool. This was great. Thanks a lot.
My pleasure. And like I said, well, if you want to dive into the code, ping me on Telegram or in Slack. Always open to talk about this. I love this kind of stuff. There's a lot of stuff that we want to do. Like I said, when you start looking at the examples, there's a bunch of stuff that will not make sense. Like why do you have to pass in this argument that always says no? Well, that's just a point that becomes a representation of a pointer to an array of system calls. You don't have to know that. There's no reason you have to know that, but that's the API the way it is today. We need to change it. And the same thing for when you want to pass in or get felts as arguments. Why do you have to pass in the limbs and not the actual felt? That's another thing that we want to change. Why do you have to serialize it as JSON and not as something a bit more efficient? That's another thing that we're going to change. and so on. So there's a bunch of work, that's laid out in the issues, and help is always welcome. You don't really need to know about compilers or MLIR or type theory or any of those things to contribute to the project. Just wanting to use it and say, hey, I tried to run this Cairo program and it blew up in my face. Can you explain why? That's also super valid and helpful.
Awesome. Thanks a lot, Aki. It was really clear and really enjoyed it. And so, yeah, if people want to learn more or work with the project or send PRs or test, whatever, it's always helpful. So thanks a lot for joining the bootcamp. And then, well, we will continue with our cryptography courses and all that, but it was really interesting for the guys to get to know about this project and its implications in the Starknet ecosystem. So thanks a lot. I really enjoyed it.
My pleasure. See you around, guys.
See you. Bye-bye.